Let's look at an example about addition principle and multiplication principle. Assume that there's a Let's assume that there's a car dealership that has a large stock of 10 different cars, that they're priced from $10,000 all the way to $100,000, $10,000, $20,000 all the way to $100,000. And we have three customers: Alice, Bob, and Charlie. Alice is happy with any car. Bob wants his car to be more expensive than Alice's, and Charlie can only afford cars that are priced at $50,000 or less. If all three of them must buy a car, then how many different ways can the three of them pick out their own cars out of all different cars that this car dealership has? So let's have a set X of all available vehicles numbered by increasing price. Let's call them X equal to 1, 2, all the way to 10, representing 10,000, 20,000, all the way to 100,000. Then the set of all different options that we have for Alice, Bob, and Charlie's cars are going to be like this. Charlie's car should be either less than or equal $50,000. Alice didn't have any requirement for her car, but Bob wants his car to be more expensive than Alice's. Okay, we want to find out how many different elements this set has. Okay, so for this set, Alice can pick any car, like from $10,000 all the way to $90,000. She cannot pick the $100,000 one, because in this set we know that Bob's car has to be more expensive than Alice's. So if Alice chooses the $100,000 car, Bob doesn't have any option, right? So here Alice has 9 different options, right? For each of these options, right, if Alice picks the first car, Bob would have 9 different options. If Alice picks the second car, Bob would have 8 different options, and so on. And finally, if Alice picks the $90,000 car, Bob would only have 1 option. Okay, so, and for all of these cases, Charlie has only 5 options, like $10,000, $20,000, $30,000, $40,000, or $50,000. Okay, so if we look at these cases, so for Charlie, we always have like 5 different options, right? But the number of choices for Bob depends on like which choice Alice has for her car. If Alice picks the least expensive car, then Bob would have 9 different options, and Charlie would have 5 different options. So in that case, we would have 45 different cases where like Alice picked the cheapest car, least expensive car. If Alice picks the second one, then Bob would have 8 different options, and Charlie still has 5 options. So in that case, we have this many options, and this can go on, right? So here we are applying multiplication principle, right? So we assume that Alice picks the first car, then Bob would have 9 different options, and Charlie would have 5 different options, so 45. Right, but Alice can pick the second one, and these 2 events are disjoint because Alice is going to choose only 1 car, right? So then we have to add it with the other options that we have, right? So if Alice picks the second cheapest car, then Bob would have 8 options Charlie would have 5 options, and this can go on. If Alice picks the $90,000 car, then Bob would only have 1 option and Charlie would still have 5 options. So if we add all these up, then we get like 225 different options that we have here. So like the number of elements in S, it's going to be 225. This is an example of both addition principle and multiplication principle. For each of these terms, we use multiplication principle, but to find the total number of elements in set S, we had to use addition principle. Now, let's talk about permutation. Let's say that we have 5 different letters, right? Okay, and we have only one of them, right? Let's say like we want to play Scrabble, right? We only have like 1A, 1B, 1C, 1D, 1E, okay? And we have 5 places, right? 5 places to put all these characters, all these symbols. How many different 5-letter words can we make out of these 5 letters? Okay, assuming that we don't have any repetition, it means like we only have one of these, one of each. Okay, so we have 5 objects and we have 5 places to put them. Okay, now how many different options do we have for the first place? We have 5, right? We have 5 letters. Okay, if we choose one of these and put it here, how many options do we have for the second place? We have 4, or 5 minus 1. How many options do we have for the third one? We have 3. And how many options for the fourth place? 2. And finally, only 1 letter is left. So how many different 5-letter words can we make? We would have 5 times 4 times 3 times 2 times 1. Okay, this is basically permutation of 5 objects and 5 places. Okay, what if we have the same letters, but this time we only have 3 spots to put them, 3 buckets to put them in? Okay, how many different 3-letter words can we have out of these 5 letters? Again, for the first spot we have 5 options, for the second one we have 4 options, for the third one we have 3 options. So we would have 5 times 4 times 3 different options. This is the whole concept of permutation. We have objects that we want to place in a sequence, in a row, like in a lineup, in different spots, different locations. We want to know how many different ways of doing that do we have. One thing that's very important about permutation, the question that you always have to ask is that, is the order important? In this case, yes, it is, right? So for example, if we have A, B, C, it's going to be different from C, B, A. It's a different 3-letter word. Those are two different 3-letter words. So in permutation, the order of the objects matters. The other question that you always have to ask, like when you're presented with a question like this, you always also have to ask, do we have repetition? Can we have repetition? Right here, I mentioned that like we only have 1A, 1B, 1C, 1D, 1E. Okay, if that's the case, we can easily answer questions like that using the formula for permutation. So there are different symbols for permutations. Like this is when we have n objects and r different places to put them, to put these n objects at. Okay, it can be shown like this, or like this. Now I want to present you with another problem. So this time I'm saying that like how many 3-letter words can we have from the, like when each letter can be picked from the English alphabet? We have 26 different letters, right? And this time I don't mention anything about the uniqueness of these characters. We have like as many as we want. So if that's the case, you have to know that like for the first option, for the first place, we have 26 different options, right? And since repetition is allowed in this example, we have again 26 different options for the second place. We have 26 different options for the third place. So for this problem, the answer would be 26 raised to power 3. Okay? So you always have to make sure that you understand the problem. Do we have repetition? And does the order matter? Okay, so that's like if the order matters, right? And we don't have repetition, we can choose, like we can use a very simple formula that's going to be given. We're gonna see that formula shortly. That's the permutation formula. If we have repetition, then we have to analyze problem like I just did, right? Like you have to do like how many options do I have for the first place, how many options do I have for the second, and how many options do we have for the third. Later on, we also see permutation when we have repetition as well. We're going to see another formula for that case as well. So let's first remember what a factorial is. N factorial would be the multiplication of all integer numbers from 1 all the way to n. So n factorial would be 1 multiplied by 2 all the way by n. 0 factorial by definition is defined as 1. Okay, so now we want to see these permutation problems when we have like n objects and n places, or n objects and k places. How can we express the express that number in terms of factorial? So let me look at this one first. We mentioned that let me actually do this. We mentioned that the number of options that we have was 5 times 4 times 3 times 2 times 1, right? What is that? This is basically 5 factorial. Okay, how about for this case, right, when you had only 3 places? This is gonna be 5 times 4 times 3. Okay, but I can express this as, let me do it here, 5 times 4 times 3 times 2 times 1 divided by 2 times 1. Okay, so basically I multiplied it by 2 and also divided it by 2, right? So the numerator would give us 5 factorial, and the denominator would give us 2 factorial. Okay, so you will see that like the general formula for the permutation, it's gonna be n factorial divided by n minus k factorial. If the number of places is the same as the number of objects that we have, that's going to be as simple as n factorial. Okay. We'll see the proof for that a little bit later. Now, we have a very special case called circular permutation. Okay, so let's look at this problem. Again, like you have 3 different people. So we want to place them on 3 different chairs, like A, B, and C. We want to place them on 3 different chairs. Okay, so now if these chairs are distinct and like they have been marked, right, and we want to like, and it like the order matters as always, and like these chairs are unique, then we can like again like have 3 options for the first chair, 2 options for the second chair, and 1 option for the last chair. Okay. So in that case, we would have again 3 factorial different ways of organizing these 3 people on these chairs. We do it like this: 3 times 2 times 1. 3 options for the first chair, 2 options for the second, and the last one, the last person is going to sit on the third chair. However, if I don't care about like these chairs like are not numbered, and I only care about the relative placement of these people to each other, right? If I only care about that, right, so we'll see like how that looks like. So we mentioned that we have 6 different ways of having these people sit on these 3 chairs, right? So like it can be shown like this. Let me actually do it like this. So we can have A, comma, B, comma, C, right? We can have A, comma, C, comma, B. We can have B, comma, A, comma, C, B, comma, C, comma, A, C, A, B, and finally C, B, A. Okay, right, these are all the 6 different ways that these 3 people can sit on these 3 chairs, right? That was for the case that we cared like who's gonna sit on what chair, right? But what if like these seats are not numbered, and we only want to know like how many different ways people can sit on these 3 chairs, like when we only care about their relative location, like who's gonna be sitting between who, right? So if that's the case, look at A, B, C, look at this case, look at this case, and look at this case, right? So in this case, if A sits here, B sits here, C sits here, right? B is sitting between A and C, C is sitting between A and B, A is sitting between B and C, right? What if it was like, what if like I just like assume that like this table is rotated, or these chairs are like rotated a little bit, like then we're gonna have BCA or CAB, right? So if in that case all these options are basically the same, right? In that case like ABC, BCA, or CAB are gonna be the same, right? And similarly ACB, BAC, and CBA are gonna be the same, right? So this is a special case of permutation called circular permutation. For circular permutation, again, let me show text box, right? So like if for circular permutation, then we just basically have to divide this by R, right? In this case, R was 3, right? So the number of ways that we can have these people sit on these 3 chairs, like where we only care about their relative location to each other, it's gonna be their permutation, which was 6, but then we only had 3 places, right? So like we have to divide it by 3 in this case, right? So like here, like if the if the chairs were not numbered, then the answer for this case would be 2, right? So just like put this example here so that you know that to answer any of the questions like this, you have to know what the question is exactly asking you, right? Is the order important? Can we have repetition, right? Does it matter who sits on what chair, or like we only like gonna look at the relative location? Okay, so like this is like an example of circular rotation that I wanted you to see. Another example here, we have 6 different colors: blue, yellow, white, red, orange, and green. How many 4-color permutation can be made if colors cannot be repeated? Okay, so again, like we want to select 4-color permutations, right? So like we have 4 places. How many options do we have for the first one? 6. How many for the second? 5, 4, 3, and that's it. Okay, so again, if you look at it, this is gonna be the same as 6 factorial divided by 2 factorial, right? Like if I multiply this by 2 and divide it by 2, I'm gonna get 6 factorial on the numerator and 2 factorial at the denominator. Okay, so here like this is basically showing that the order like of the colors is important. So blue, red, yellow, green is going to be different from blue, red, green, yellow, and also mentioned that there is no repetition, so we can't have blue, 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 right? Another example, a club of 9 people wants to choose a board of 3 different officers. One is going to be president, 1 vice president, and 1 secretary. How many different ways is this possible, right? How many different ways can we have a committee of 3 out of 9 options that we have? Again, for the president, we have 9 options. For the vice president, because like we picked 1 person for the president, we would have 8, and for the secretary we would have 7, right? So this is the case where n is equal to 9 and r or k is equal to 3. We have n objects, 3 places to put them. Okay, and again, look at it. I can show this one as 9 multiplied by 8 multiplied by 7 multiplied by 6, 5, 4, 3, 2, and 1, and I'm gonna divide it by 8, just divide it by 6 multiplied by 5 multiplied by 4 multiplied by 3 multiplied by 2 multiplied by 1. Not braces. Okay. So I basically multiplied this one by this multiplication. I also divided it by the same number, right? If I do that, then this is going to be 9 factorial divided by 6 factorial. Okay, this was the case that n was 9 and k or r, whatever you name it, was 3, right? So, and we mentioned the formula for permutation is basically n factorial, you see like it's 9 factorial, divided by n minus k factorial, right? So here it was 9 minus 3, which is 6 factorial. Okay, now we show the permutation number using this formula because it's just like more compact. It's not efficient to calculate though. This is definitely way more efficient than doing this calculation, right? So this is much more efficient like than just like doing all these multiplication and then doing all these divisions, right? This is just a short format to make it easier to remember. How many unique ways are there to arrange the letters in the word iron. So these are four distinct or four different letters, right? And we only have one of them, right? So this is going to be, again, like for the first one we would have four options, then three options, then two, then one, right? So this is like basically permutation of, like I can write it like this, 4p4, or let me make this one bigger, or like make these ones subscript. Okay, or it's going to be 4 factorial. Okay. Here, like, we have 4 different objects and 3 different places, right? So the answer to this question would be 4 times 3 times 2, okay, which is going to be the same as saying 4 factorial divided by 4 minus 3 factorial, which is just 1, right? So this is like the general formula for permutation. Here, like, this was 4 factorial divided by 0 factorial, which is, or like, which was like, sorry, 4 minus 4, which is 0 factorial. And this is 1, so it's going to be again 1. So in math, the notation of permutation relates to the act of rearranging objects or values. A permutation of a set or a subset of objects is an arrangement of those objects into a particular order, right? Order is very important in permutation. Consider the problem of arranging a group of people in a row, right? So like all these problems can be, we can have an analogy like this, just like arranging group of people in a row. 2 factors to keep in mind when counting the number of possible arrangements. Choosing a person from the group changes the number of options available in the next choices, in the successive choices. The order in which they are arranged is significant. It is important. For example, how many different ways are there possible for arranging 2 out of 3 elements in set A, B, C, right? So we can have A comma B, or A comma C, or B comma A, or B comma C, CA, or CB. 6 different ways. Okay, so here you have 2 places but 3 objects, right? So again, based on the formula, it's going to be 3 factorial divided by 3 minus 2 factorial. So it's going to be 6, right? Which you can see all the 6 ways of rearranging them. The number of ways of obtaining an ordered set of R elements from a set A containing L elements is called R permutation of set A. R permutation of set A. We have R places of set A and is denoted as PNR. In the previous example, we had 3 elements in the set and we only had 2 places, right? So like it was 2 permutation of set A was like, that's why it was 6. This basically shows all the places that we have, right? All the places that we have 1, 2, 3, like we just like labeled them. We have R places. For the first place, we have n options. For the second one, we have n minus 1. For the third one, we have n minus 2. And if this goes on, for the last one, we would have n minus r plus 1 different options to pick from for the last one. Okay? Because we basically used r minus 1 objects and they're placed here. So for this one, we would have n minus r plus 1. Okay, so if we multiply all of these together, right, so we can actually calculate this by, this is again like based on multiplication principle. excuse me. And the short format of that would be n factorial divided by n minus r factorial. And you know the definition for factorial. If r is 0, then like how many options do we have for just rearranging nothing out of like n elements? Just like one way, and just like doing nothing, right? And if in the special case where r and n are equal, then the formula is reduced to a very simple format of n factorial, because 0 factorial is equal to 1. Okay, so let's look at this quiz, or like this practice question. In how many different ways can 8 people stand in a line if there are no restrictions? No restrictions. So in this case, right, we have 8 different people. We want to have them in a row, in a lineup. How many different ways can we do that? Again, for the first place, we have 8 options. For the second one, 7. For the third one, 6, and so on. So it's going to be 8 factorial, or this is basically p of 8 and 8, right? We have 8 places and we have 8 objects, right? So the answer would be option A. Okay. Now, what if we have another restriction, right? We want to place 8 people in a row, like in a line, right? So like assuming that close to a wall, like we have 8 different places and we want to put 8 people in these places, right? Like we basically want to line them up. And Alice and Bob, they're lovey-dovey, they're lovebirds, they want to be close to each other, right? So in that case, how many different options do we have? In how many different ways can we have these 8 people stand in a line, right? If Alice and Bob have to be close to each other, have to be standing next to each other. Okay, so think about this one. Right, so there is a restriction here, right? One way to solve this problem is that we just assume that Alice and Bob are just one person, okay? Because they have to be standing next to each other, so like we can just like basically assume that they're attached to each other, right? So like we can count them as one person, right? So in that case, we end up with 7 different people, right? And we want to place them in a row. So we would have a rotation of 7 people and 7 spots, right? So it's going to be P of 7 and 7. However, what we didn't consider is that Alice and Bob, they're 2 people, right? So they also can have permutation. Like they can just like Alice can be standing on the left of Bob, or can be standing on the right of Bob. So it can be Alice Bob or Bob Alice. So for all of these permutations that we have, right, we have to multiply it by the number of permutations that we have for Alice and Bob, right? Because in each of these cases, Alice can be either on the left or right of Bob, right? So that's why the answer for this one is option B. Right? So one thing that we did, we just assumed that Alice and Bob are basically the same person, right? But then we also have to consider their permutation, right? There are 2 objects, right? How many different ways of placing 2, the 2 people, sorry, they're not objects. The 2 people, how many different ways can we line them up, right? It can be 2 factorial, or 2 ways. Alice Bob or Bob Alice, right? So that's how this is the answer for this question. In MATLAB, we can implement permutation. We can find the answer using a function handle, right? So like let's say that I want to find like what is the permutation of having 5 people and like 3 spots, 3 locations. I can use a function handle. We have the factorial function. I can calculate n factorial and n minus r factorial. But is this really efficient? Is this really efficient? To answer this, let's look at this. What if n is 1000 and r is 2? Then n factorial would be 1000 factorial and 998 factorial. Sorry, is n minus r. N minus r is 998 in factorial. Okay, we could simply we simply know the answer, right? Like if we have 1000 people and we have only 2 spots, we only have like 1000, we have 1000 options for the first spot and 999 for the second one, right? So this is the answer. This is the short form of showing it, right? N factorial divided by n minus r factorial. But is it easy to calculate? Now 1000 factorial is a very, very huge number, right? So in most cases, your software or your code, your programming language is going to give you an overflow error, right? Because they cannot show this one, right? So it's basically like to answer this question, we only need to do one multiplication, but we are doing like so many more. Like we are doing like 999 multiplications here, 997 multiplications here, and then a division, right? So we didn't need to do that. So this is not a very efficient way of finding the number of permutations that we have using MATLAB. Another way of doing it is just like basically using what MATLAB is good with, like which is matrices. So what we do, we create one matrix, right, which is gonna have n elements, like it's a row matrix or a row vector, sorry, a row vector. It has all the elements from 1 to n. Okay, and we're gonna do element-wise division. Like you remember that we can do element-wise operations on matrices if they have the same size, right? So first of all, we're gonna make another matrix with the same size as the first one, right? So here we start the second matrix by like its first n minus r elements are going to be the same as the matrix on top, the matrix in the numerator. Okay, so here like we have 1 2 3 4 5 6 all the way to n. This one starts like that, 1 2 3, but it goes all the way to n minus r, and for the rest of the elements you're going to place 1. Okay, so this is basically showing the numerator. It goes like from 1 to all the way to n minus 1. In the denominator, we have 1, 2, all the way to n minus r. And for the rest of the elements, we place 1. Okay. Now, what's going to happen if we do element-wise division, right? So 1 divided by 1, it's going to be 1. 2 divided by 2, 1. 3 divided by 3, 1. N minus r minus 1 divided by this, it's going to be 1. N minus r divided by n minus r, it's going to be 1. And then, right, everything in the numerator matrix is going to be divided by only 1. So like everything here, it's going to be coming here, n minus r plus 1, n minus r plus 2, all the way to n. So this matrix is the is basically what we have here in this element-wise division. Another way of doing this would be, let me show you again what sorry, like this one. I could also make the same matrix by saying that we would have ones of 1 comma. So here, look at it. We will have n minus r ones. So it would be 1 minus n minus r. Okay. And the rest, it's going to be n minus r plus 1 all the way to n. So let me actually do this one like this. So okay, so instead of like calculating n factorial and n minus r factorial, we basically just do this. And like if we don't like want to do this division, like this is not even necessary, right? So like we can just like say that I want to find the product of these elements, like from n minus r plus 1 all the way to n, right? So this is the easier way of finding the permutations in MATLAB. Basically just like these calculations, instead of like doing all these calculations and then dividing it by n minus r factorial. Okay, so either of these would be efficient, right? This is definitely way more efficient, but you have to make sure that your n is bigger than or equal r, excuse me. Okay. A function in MATLAB that gives you different permutations of a set would be perms. So for example, if we do like here, if x was 135, perms of x would give us, you can try it, but it would give us like 135, 153, 315, 351, 513, and 531. The same thing for A, B, C, D, E. So it would give us 5 factorial different permutations of these 5 letters. Okay. There's a question for you here. How many possible permutations of a set of 3 elements we can have right here? Like you see that like we have 6, right? It's 3 factorial. Now, I mentioned that there is a subcategory of permutation called permutation with repetition. Okay, so here, let me go back to, let me ask you this question. How many different letters can we, how many different permutations can we have out of the letters in this like word, like which is ABC? Let me actually find like a just a cap. That's actually a meaningful word. So how many different 3-letter permutations of characters in the word cap can we have, right? So this was, we saw that we can have ABC, ACB, BAC, BCA, CAB, and CBA. Okay, which was 6, right? And it was 3 factorial, right? What if I give you this one? How many different let me say like ABBA. So I was born in 80, so ABBA. Okay, so let's see how many permutation of characters in the word ABBA can we have, right? So here we have repetition. We have 2 A's and 2 B's, right? If these A's were different, like if I called this one A1 and this one A2, and the same thing for B1 and B2. If these A's and B's were different, then we would have 4 factorial different permutations. Okay, but these ones are actually the same, right? The A's are the same, the B's are the same. Okay, and so let's say that, like, if we have like ABA, right, as just one of the permutations, right, I'm counting it twice only because we have, like, I counted it twice because, like, we have 2 similar A's, right? Because I counted it as A1 B's and A2, and then A2 B's and A1, right? So there were like 2 factorial permutations for A's, and because of that, in these 4 factorial number that I got, means that, like, I counted options twice of what it should be, right? So, like, I actually have to divide it by 2 factorial because of the 2 A's that we have. Okay, and we also have 2 B's, like 2 similar B's. So again, I have to again, like, divide it by another 2 factorial because of the 2 B's that we have. So this is called permutation with repetition. So suppose we have the string happy. How many different permutations are there for these 5 letters? So again, if the P's in this string or in this word were different, if I call them P1 and P2, right, then you would have 5 factorial different permutations, right? But in that 5 factorial permutations, let me say, like, this is like what we have: P1, P2, hey, right? This is one of the permutations, and then this one is going to be another one. Right? So this was counted twice, right? This was counted twice. Like these P's are actually the same. There is no P1 and P2, like they're P's, right? So, like, if I just remove these indices, then you see that, like, these two are the same. So in this 5 factorial, this word was counted twice because there are 2 factorial permutations for the 2 P's that we have here. So to find the answer here, we have to say 5 factorial divided by 2 factorial. Okay, so switching the position of the P's would not yield a new arrangement since P's are not distinct. We have 5 factorial possible permutations if there are no repetitions. If we have repetitions, that number should be divided versus possible repetitions. Okay, how many different repetition permutations can we have for 2 P's? We can have 2 factorial. Okay, in general, in a permutation of R objects, if we have R1 instance, Ri, R sub I instances of type I, we have these many permutations with repetitions. To show you an example of this one, there's a very famous example. We're gonna see that one. So, like, say, like, in this string, right, the string Mississippi, how many different permutation of the letters in the word or in the string Mississippi can we have? right? There are 11 different letters, 1 2 3 4 5 6 7 8 9 10 11. So like if all the letters were distinct, we would have 11 factorial different permutations. But how many repetitions do we have for i's? We have 4 i's. These i's can have like 4 factorial different repetitions, right? So we have to divide this 11 factorial by 4 factorial because of the i's. We also have 4 s's, so we also have to divide it by another 4 factorial for the s's. We also have 2 p's, so we have to divide it by 2 factorial for the p's. Okay, so that's what the permutation with repetition is. Okay, I'm gonna continue with the combination in another video. Thank you so much.